And right, good morning. All right, next week, Wednesday is a holiday, so we won't have class then. It's Veterans Day, November 11th. Okay, we're going to begin a new chapter today. And this will be on carboxylic acids. All right, the functional group for a carboxylic acid is also called the carboxyl group. Sometimes we write it as RCOOH, although I prefer to draw out the Lewis structure. We have both aliphatic and aromatic carboxylic acids. Right, to name a carboxylic acid, we drop the E from the parent alkane, and then the suffix is oic acid. Carboxylic acids have the highest priority of any functional group, and other substituents will fall where they may. It's assumed that the carboxylic acid group is on carbon number 1. Okay, so this is, let's say, butane, butanoic acid, and then there's a methyl on carbon number 3, so 3-methyl butanoic acid. The common name for this is isovaleric. Okay, and we'll talk a little bit about common names shortly. Okay, this is trans-3-phenyl propenoic acid. Okay, propane. We don't need to say 2-propenoic acid because in this particular case, the double bond has to be between 2 and 3. Okay, and then phenyl, of course, is a benzene ring as a substituent. Okay, this is cinnamic acid. The corresponding aldehyde, cinnamaldehyde, is one of the major components in oil of cinnamon. Okay, as I mentioned, the carboxyl group takes precedence over most other functional groups. Okay, the only exception we haven't covered is sulfonic acids, but we won't see any examples of those. Okay, so here we have an alcohol, an amine, and a ketone as substituents. So 3-hydroxyhexanoic acid, 4-aminobenzoic acid, and 4-oxohexanoic acid. Dicarboxylic acids, okay, we would add the suffix dioic acid. So this is ethane dioic acid. We could say 1,2-ethane dioic acid, but we don't need to because the carboxylic acids have to be at the end of a chain. Okay, so we have propane dioic or malonic, butane dioic, pentane dioic, and hexane dioic. These are widely known by their common names. Okay, especially oxalic and adipic. Okay, just like with aldehydes, carboxylic acids cannot be part of a ring. They have to be outside of a ring. If a carboxylic acid is attached to a ring, then we have the suffix carboxylic acid instead of oic acid. All right, so this is 2-cyclohexene carboxylic acid. Okay, here the point of the ring where the carboxylic acid is attached, that's carbon number 1. Okay, and then this is trans 1,3-cyclopentane dicarboxylic acid. Okay, it's not correct to call it cyclopentane dioic acid. Okay, that implies that we have fewer carbons. We only have 5 carbons. Systematically, benzoic acid should be called benzene carboxylic acid, but nobody calls it that. Benzoic acid is accepted in the IUPAC. 2-hydroxybenzoic acid is commonly known as salicylic acid. Okay, this is 1,2-benzene dicarboxylic acid. This one is more commonly known as phthalic acid, PHTHALIC. And then 1,4-benzene dicarboxylic acid is called terephthalic acid. Okay, in the United States, terephthalic acid is much more commonly used. Okay, you may see this if you happen to look at very old articles or old textbooks. You may see common names with alpha substituents. Just like with ortho, meta, and para, we use these Greek letters to specify relative positions. This is alpha to the carboxylic acid. This position is beta, gamma, and so forth. 4-aminobutanoic acid is also known as gamma-aminobutyric acid. Okay, notice the common name is slightly different. This is GABA. This is actually a neurotransmitter. All right, in common nomenclature, keto indicates the presence of a ketone. We're going to use oxo, which is the IUPAC. So this is 3-oxobutanoic acid. And then this substituent is called an acetyl group. Okay, in omega-3 fatty acids, the last carbon of the last double bond of a hydrocarbon chain ends 3 carbons from the methyl terminal of the chain. Okay, so that's what omega-3 means. You go to the far end of the chain, and then at the 3rd carbon from the end, you have a double bond. Okay, icosapentaenoic acid is a common polyunsaturated fatty acid found in cold water fatty fish and health food supplements. Okay, how many cis-trans isomers are possible? Okay, we have 5 double bonds. None of them are at the end. So there's actually 5 pairs of cis-trans isomers. It turns out that in the natural product, these double bonds are all cis. Okay, in terms of physical properties, in the liquid and solid states, carboxylic acids are associated by hydrogen bonding into dimeric structures. Okay, so here's a hydrogen bonded dimer. Carboxylic acid can both accept and donate a hydrogen bond. Okay, these hydrogen bonded dimers are so strong that for lower molecular weight carboxylic acids, they're even intact in the gas phase. Okay, and because of this ability to hydrogen bond, both by donating and accepting in two different parts of the molecule, carboxylic acids have a significantly higher boiling point than other organic compounds with comparable molecular weight. They're polar compounds. They form very strong intermolecular hydrogen bonds. They are more soluble in water than alcohols, ethers, aldehydes, and ketones with comparable molecular weight. Okay, and that's because they form hydrogen bonds through both the CO double bond and the OH groups. Right, so here is decanoic acid. And just like with most of our other functional groups, okay, water solubility goes down as the size of the carbon chain goes up. Okay, and I think this diagram illustrates that well. Okay, we've got this polar end, but you notice most of the molecule is this nonpolar hydrophobic tail. And so decanoic acid, 10 carbons, is only 0.2% soluble in water. Okay, it has a polar head, but most of the molecule is this hydrophobic tail, and the London dispersion forces tend to dominate. Right, here is one of the most important things to remember about carboxylic acids is that they are weak acids. Values of the pKa for most aliphatic and aromatic carboxylic acids fall within the range of about 4 to 5. Okay, and once again, this is the expression for Ka. It is the conjugate base times the hydronium over the undissociated acid. Okay, and for acetic acid, this is the value of the Ka, and then the pKa is minus the log of that, 4.76. All right, the greater acidity of carboxylic acids compared to other functional groups is because this conjugate base is now resonance stabilized. Right, if we have electron withdrawing groups nearby, okay, such as halogens, these will increase the acidity through the inductive effect. Okay, so here we have acetic acid, and if we replace one of the alpha hydrogens with a chlorine to form chloroacetic acid, okay, that's almost a 100-fold increase in acidity, 2 pKa units. Okay, if we have 2 chlorines, you can see that that has an even greater effect. And then for trichloroacetic acid, right, 0.7 versus 4.76. Okay, this is 4 pKa units, or 10 to the fourth, or 10,000 times more acidic than acetic acid. Okay, the inductive effect, as a reminder, that involves pulling electrons through the sigma bonds. And if we form an anion, okay, an electron withdrawing group such as a chlorine will help stabilize that anion. So this anion is stabilized both by the inductive and by resonance effects. Okay, this slide illustrates that the effect drops off with increasing distance. Right, so here we have butanoic acid. Okay, that's 4.82. Okay, that is not much different from acetic acid. Okay, 4.76. Okay, so extending the carbon chain really doesn't affect the acidity noticeably. Okay, and then we have, okay, I'm going to start over here on the left, 2-chlorobutanoic acid, 2.83. Again, just like with the acetic acid, that's about a 100-fold increase in acidity. Okay, but as the chlorine gets farther away, it has less of an effect. And by the time that chlorine is out here to the 4th carbon, there's very little effect. Right, carboxylic acids are, some of them are water soluble, some of them are insoluble, but they will react with sodium hydroxide, potassium hydroxide, and other strong bases, and even things like sodium carbonate to give water soluble salts. Okay, when you did the extraction lab, okay, benzoic acid is only slightly soluble in water, and you had that dissolved in methylene chloride. When you did an extraction with sodium hydroxide, that converted it to sodium benzoate, okay, which is now 60% soluble in water. And then you may remember that you later took that aqueous phase, and we added strong acid, or you added strong acid like HCl to it, and that reversed it, producing benzoic acid, which precipitated, and you collected that by suction filtration. Okay, remember when we talked about ammonia and amines that they were weak bases. All right, so carboxylic acids can react with ammonia and amines to form ammonium salts. Okay, so here we have benzoic acid, again, just slightly soluble in water, but the salt ammonium benzoate now is 20% soluble in water. Okay, we produced a species that has charged groups, okay, which would render that ion more soluble in water. Right, sodium bicarbonate will also react with carboxylic acids. Sodium bicarbonate is baking soda. Will also react with sodium carbonate to form water-soluble salts and carbonic acid. The carbonic acid, though, is not stable, and it breaks down to form carbon dioxide and water. All right, so here is the vinegar and baking soda reaction. Okay, acetic acid is a component of vinegar. Okay, we react that with baking soda, and we get sodium acetate, and the carbonic acid then breaks down into carbon dioxide and water. Right, so we could use this acidity to separate carboxylic acids from other compounds with different functional groups. Okay, for example, we could separate benzoic acid from benzyl alcohol. Okay, both of these would dissolve in diethyl ether. If you do an extraction with 0.1 molar NaOH, okay, nothing happens to the benzyl alcohol. It stays in the ether layer. And so if we evaporate off the ether, then we recover the benzyl alcohol. Okay, the water layer, though, will contain sodium benzoate. So extracting with sodium hydroxide will render the benzoic acid more soluble in the water layer. Okay, so we separate the layers. If we add acid to the water layer, that reprecipitates the benzoic acid. Carboxyl group is very resistant to reduction. Okay, it is not affected by catalytic hydrogenation under conditions that reduce aldehydes and ketones, or alkenes and alkynes to alkanes. Carboxylic acids are not reduced by sodium borohydride. Okay, they can be reduced with lithium aluminum hydride, which is a stronger reducing agent than sodium borohydride. The product will be a primary alcohol. Right, so reduction, we carry this out in diethyl ether, THF, or other non-reactive aprotic solvents. Okay, we start out with 3-cyclopentene carboxylic acid. And, okay, following the reduction, we get the corresponding primary alcohol. Okay, and this is called 4-hydroxymethyl cyclopentene. Okay, byproducts are lithium hydroxide and aluminum hydroxide. Okay, so the main point here down at the bottom was that the lithium aluminum hydride reduced the carboxylic acid, but notice it left the alkene group alone. Okay, conversely, if we use catalytic hydrogenation, okay, that has no effect on the carboxylic acid group, but you can see that it does reduce the alkene. Okay, another example of selective reduction. Okay, here we have 5-oxo-5-phenylpentanoic acid. We've got a carboxylic acid on the right. We've got a ketone benzene ring on the left. Okay, using sodium borohydride, all right, the ketone is converted to a secondary alcohol. The carboxylic acid group is unaffected. So we now have 5-hydroxy-5-phenylpentanoic acid. Right, another reaction of carboxylic acids is the preparation of esters. Okay, one of the experiments that we often do in organic lab is preparation of banana oil. Have you guys done that? No, okay. So you might do an esterification, and that uses isopentyl alcohol instead of ethanol here. But we use ethanoic acid or acetic acid and ethanol. And then there is a catalyst, sulfuric acid, that's added. The product is an ester. Okay, so notice what happened. Color-coded in purple here, we have an OH and an H. So water is split out. And then the two groups, the unshaded and the blue-green, are reconnected to form an ester. Okay, this is an equilibrium reaction. Okay, so even if we use stoichiometric amounts of carboxylic acid and alcohol, okay, we may not, in fact, we usually don't get quantitative yield of ester. Okay, but we can manipulate experimental conditions. Usually what's done in this type of esterification, this is called Fischer esterification, is to use an excess of either the acid or the alcohol. And often what determines that is if one of them is inexpensive. Okay, so this is Le Chatelet's principle. Okay, and it frequently takes a long time to reach equilibrium. Okay, maybe an hour or several hours. Okay, so we rarely use one-to-one stoichiometry in this. Instead, we'll use an excess. If we add one of the reactants, that the equilibrium will shift toward products. Right, a key intermediate in the Fischer esterification is this tetrahedral carbonyl addition intermediate. Right, so oxygen here, this oxygen picks up a proton, and the alcohol then adds to the carbonyl, and then we have loss of a proton. Right, if we replace the OH of a carboxylic acid with a halide, and this is usually a chlorine. It is possible to have acyl bromides, but they're much less commonly used. Okay, so here are some examples. Acetyl chloride or ethanoyl chloride, and then this is benzoyl chloride. Right, if an acid chloride is not commercially available, one way of preparing it is with this reagent called thionyl chloride. Okay, you may remember we use this reagent to convert alcohols to alkyl chlorides. We can also use it to convert carboxylic acids to acyl chlorides or acid chlorides. Acyl chloride is a more precise term because phosphoric acid and sulfuric acid and a number of acids can also form acid chloride. So acyl chloride specifically refers to those from carboxylic acids. Okay, this reaction works very well. Okay, the byproducts, SO2 and HCl, are both gases, so they can be easily removed. Right, another reaction is called decarboxylation. Okay, what decarboxylation means is loss of carbon dioxide from a carboxyl group. Okay, generally, for most carboxylic acids, this is difficult to do. It requires a really high temperature to decarboxylate a carboxylic acid. Okay, most are quite resistant to decarboxylation. All right, exceptions are those carboxylic acids that have a carbonyl group that is beta to the carboxyl group. And that is either a ketone, as shown here, 3-oxobutanoic acid, or it could also be a carboxylic acid at this point. Okay, so remember, here's the carboxylic acid, this is the alpha, this is the beta position. So if we have a ketone at the, or a carbonyl at the beta position, okay, this can be easily decarboxylated just with mild heating. Okay, so we lose CO2 and our product here is acetone. Okay, this goes through a cyclic transition state. Okay, the reason that beta carbonyl carboxylic acids undergo this decarboxylation is it goes through this six-membered ring. Having the carbonyl at any other position doesn't favor this cyclic intermediate. Okay, so I'll walk you through here. The pi bond in the carbonyl group grabs this hydrogen. This pair of electrons then moves to form a double bond. This bond breaks, it moves this way. And that gives us carbon dioxide. We form a double bond here, we break this bond. And then we initially form this enol. Okay, in the last chapter we talked about enols. That's where you have an alcohol directly attached to an alkene. Most enols are not stable, so this one is going to rearrange to form acetone. Okay, so that is with that's with a beta keto acid. This is with malonic acid or propane dicarboxylic acid, dioic acid, sorry. Okay, that also forms the same cyclic six-membered transition state. All right, so this is, if you look at this, this is a beta keto acid. Okay, this is the alpha, this is the beta. Okay, this would go through a cyclic transition state when we heat it. All right, so we'll lose carboxylic acid, we'll lose carbon dioxide, and product that would be cyclohexanone. All right, the second problem gives us this as the product. Okay, so if we heat something, we get this plus CO2. All right, so where is the carboxylic acid? Okay, so here's alpha. It would have to be here. No. Oh, actually, that would have to be here. Okay, and then here's alpha, here's beta, and we lose CO2, we would get that product. All right, so that is the end of chapter 13. What I want to talk about next are some of the common names and their origins. at the simplest carboxylic acid, where R is an H, this looks like maybe it could be an aldehyde, but it's actually a carboxylic acid. It behaves like a carboxylic acid. I'll give you both the IUPAC and the common. So this is methanoic acid. And the common name is formic acid. And the origin of this name comes from the Latin word formica, which means ant. This is what makes the bites of fire ants so painful. Formic acid is also present in bee stings. Even if you open a bottle of concentrated formic acid, okay, it starts to actually burn your wrists if you're not wearing gloves. The next one is acetic acid. That over here. Okay, this is acetic acid. Its IUPAC would be ethanoic acid. Okay, I'm omitting the word acid just to save some time here. Acetic acid, again, comes from a Latin word acetum, which means vinegar. Vinegar is about a 4 to 5% solution of acetic acid. Distilled white vinegar is just acetic acid and water. Apple cider vinegar or wine vinegar also contains fermentation products from apples or grapes. Okay, so 3 carbons. In the IUPAC, this is propanoic. Propane, we drop the E. So this becomes propanoic acid. And the common name is propionic acid. Propionic comes from a Latin phrase meaning first fat. This was originally isolated from butter fat, from the breakdown of butter fat. Okay, propanoic or propionic acid is one of the compounds most responsible for the odor and flavor of Swiss cheese. In the IUPAC, 4 carbons would be butanoic acid, and the common name is butyric acid. Again, very similar. The name butyric comes from butter. All right, when butter goes rancid, the butter fat breaks down and it produces, one of the compounds it produces is butyric acid. Butyric acid is a terrible smelling compound. When butter goes rancid, you know without a doubt that it is rancid. This smells like vomit. You might have also smelled butyric acid if you've been around someone that hasn't showered in a while. Okay, when the bacteria break down the oils in the skin, this is one of the components of human body odor. And it turns out that many dogs are very sensitive to this odor. They can detect very small amounts of this. And this is one of the compounds that dogs can detect that enables bloodhounds to track someone, to find their trail, or to find someone buried under snow. And then, of course, dogs can be trained to sniff out other compounds as well, from, say, from decomposition. Pentanoic acid, also called valeric acid, okay, from the valerian root. And then hexanoic acid is caproic acid. Caproic comes from Capricorn, meaning goat, and caproic acid is produced from goat glands. Okay. 2-hydroxybenzoic acid is commonly called salicylic acid. The name salicylic acid comes from salix, which means willow. Okay, this goes back to ancient Roman times. The Romans recognized that parts of the willow tree, leaves and bark, for example, contained a pain-relieving ingredient. And it was in the 1800s that this component was called salicin was isolated, and it was modified to produce two pain-relieving compounds. Acetylsalicylic acid is aspirin. Okay. And that looks like this. Okay, we have an ester and a carboxylic acid. That's aspirin. Then if we form the ester group here, okay, that's called methyl salicylate. Methyl salicylate is a main component of oil of wintergreen. It's an active ingredient in Bengay and other liniments. Aspirin does contain a carboxylic acid group, and so aspirin has to be buffered. If it's too acidic or too basic, it can really cause damage to the digestive system. Okay, and then I'll mention one more. This one is ethane dioic acid, is also called oxalic acid. Oxalic acid is found in spinach and rhubarb and a number of other natural products. Okay, many carboxylic acids that are found in food, such as citric acid, acetic acid, tartaric acid from grapes, these all have a sour taste. Oxalic acid is really sour, so if you ever use rhubarb in cooking, you know you have to add a lot of sugar because this is really, really sour. All right, that is all of our time for today. I'm going to go ahead and end there.